All right, guys, let's think about some general equations of planes. Now that we have the normal vector and this idea of the direction vector, we can actually think about the intersection of planes in a little bit of a different way than the way we were thinking about it before. So we're going to do one of those finding a consistency condition problems, but we're going to ask a few more questions and we're going to talk a little bit more about what all of the answers mean. So the first thing we're asked here is we have a system of two planes. So I'm going to name these planes. We'll call this one plane 1. And this one plane 2. And the first thing that we want to do is find the normal vectors of these planes. So that is the most straightforward thing. The normal vector of the first plane will be 1, 3, k. So I'm just looking here at my coefficients of x, y, and z. The normal vector for my second plane here will be 2, 6, and 5. And here I'm just looking at the coefficients of the second plane. So that 2, that 6, and that 5. So that gives me my normal vector for the second plane. That's it. That's A. We have our normal vectors. Now I want to find the values of k, if any, such that the planes are orthogonal. Well, the planes will be orthogonal if the normal vectors of the planes are orthogonal. So B, planes are orthogonal if their normal vectors are orthogonal. Okay, so let's think about why that's the case. I'm just going to draw some planes. A lot of times it's going to be helpful to draw planes as just straight lines. I know that seems a little bit weird, but in these things, it really does help to visualize what's going on. And it's really hard to draw a plane because you want it to kind of be in like 3 dimensions, sticking out of the iPad, sticking out of your paper, and that's really hard to do. So I'm going to call this thing right here plane 1. And I'm going to think about it as just a line. And my normal vector for plane 1 that we found is going to be that. And then I'm going to call this other plane, plane 2. And what I want is for these two planes to be orthogonal. So I'm going to draw this plane 2 as being orthogonal to plane 1. But notice, when I draw my normal vector, my vector that's perpendicular to the plane, it ends up being perpendicular to N1. So if P1 and P2 are perpendicular, then N1 and N2 are also perpendicular. And how do we determine if two vectors are perpendicular or not? We do the dot product. And we know that in order for two vectors to be perpendicular, their dot product has to equal to 0. So what that means here is we need to find k. In other words, another way of stating this question is find k such that N1 dot N2, the dot product of the two vectors, is equal to 0. So let's do that. N1 dot N2 is equal to 1, 3, k dot 2, 6, 5. And I want this to equal to 0. So that gives me 1 times 2 plus 3 times 6 plus k times 5 is equal to 0. So that's 2 plus 18 plus 5k is equal to 0. So 5k is equal to negative 20, which tells me that k is equal to negative 4. So in other words, these planes are orthogonal if k equals negative 4. All right, so orthogonal if k equals to negative 4. And think about it. If I have two planes that are orthogonal, that means I'm going to try to draw my actual planes here. So I have this plane, and then I have this other plane that's sticking out of it. And then it's going to go through, because remember, planes go on forever. The intersection of those two planes right there is going to be that line kind of through the middle. So in other words, if I think about this in terms of two pieces of paper, these are my planes. Look, they're orthogonal to each other. We have to assume that the blue is piercing the green plane and continues going on forever on the other side. Notice the shape of intersection there is a line, and that's going to be important in just a second. So the intersection there is a line, which means there are infinite points in common. Yay. Okay, the next question said, to find the values of k such that the planes are parallel. So this, my planes are going to be parallel if their normal vectors are parallel. Okay, so let's just draw a picture to see what that means. Again, I'm going to draw these planes as line because you see what it looks like when I try to draw planes as actual planes. So my first plane, P1, I draw. Then I have my normal vector, that's in 1. Now I want, in this case for P2, to be parallel to P1. So I'm going to draw it parallel, and notice, in this case, my normal vector will be parallel to the first normal vector. So in other words, we can say that P1 is parallel to P2 if N1 is parallel to N2. So what does it mean for vectors to be parallel? If they are scalar multiples. So in this case, we need to find k such that those two vectors are scalar multiples, if possible. So find k such that N1 and N2 are scalar multiples. So in other words, we're saying my first vector here was 1, 3k and then 2, 6, 5. So I want to have some constant times 1, 3k is equal to 2, 6, 5. Well, the only constant that could possibly make this true is 2, because I need to multiply c by 1 and get 2. I need to multiply c by 3 and get 6. So the only possible c here, the only possible constant is c is equal to 2. So now we have 2 times 1, 3k is equal to 2, 6, 5, which gives me 2, 6, 2k is equal to 2, 6, 5, which tells me that 2k needs to equal to 5, k equals 5 over 2. So the planes are parallel if k equals 5 over 2. So note that in this case, this idea of parallel of k equals 5 over 2 is not eliminating the possibility that these are actually the same plane. So what that means is these planes have the same slope. So like if two lines have the same slope, either they're parallel or they're the same line. So in this case, we're saying the planes are parallel if k equals 5 over 2. So either if k equals 5 over 2, either we have this case where, again, I'm just going to draw my planes as line. I have plane 1 and I have plane 2, and they're parallel. And if those two planes are parallel, so they have the same direction, then they don't touch anywhere, right? So those two planes are just never going to touch. So it's not like I have one that kind of comes down an angle at the other. They're parallel, they just never touch. So here, this would be no intersection. And then the other possibility is if k equals 5 over 2, either they are parallel, no intersection, or I have P1, notice P2 could potentially have the same slope and still be the same plane. So here they could be the same plane. And if they're the same plane, then yes, they're still parallel. But if they're the same plane, how many points do they have in common? Well, every point. They touch everywhere. And the shape of everywhere is just a plane. So here, this would be intersect in a plane, infinite points in common. Okay, so again, we're going to kind of use this to do the last question, or really to talk about the last question. All right, so I know that my normal vectors, I got my normal vectors. I have k equals -4 to make my planes orthogonal. I have k equals 5 over 2 to make my planes parallel. Now, for the last question, I'm really doing a consistency condition question. Find the values of k such that the planes intersect in a line, a plane, a point, and not at all. So I'm actually going to go about doing this question in the same way that I did my consistency condition questions. There are now two ways I could approach it. And we're going to talk about the second way, but really the best way to approach it is the way that we're about to do right here. So what we would do for a consistency condition question is take the plane and stick it into a matrix and then reduce to REF. So I'm going to reduce to REF, which means that really all I have to do here is do row 2 minus 2 times row 1. And that's going to give me 1, 0, 3, k, 6. Actually, I'm going to go to the next line to do this. My first row is not changing. 1, 3, k, 6. Then I'll have a 0 here. I'll have a 0 here. I'll have a 5 minus 2k here. And then I will have h minus 12. So same as before, we want to first check for an obvious contradiction. Is there an obvious contradiction? Remember, that would happen in the case of 0, 0, 0, not 0. Well, I don't have that row of zeros on the bottom, so maybe there's a contradiction somewhere, but it's certainly not obvious. No obvious contradiction. Now, the next thing I want to do here is notice that this 5 minus 2k right here is in a pivot position. This k is not in a pivot position. Not in a pivot position, which means that it does not matter to me. It's not important. I'm not going to think about it at all. I'm only thinking about that 5 minus 2k. Okay, so for one, I want to know the planes intersect on a line, a plane, a point, or not at all. Let's just write that down. Line, plane, point, not at all. Well, in order to intersect in a point, that would be one solution, which would mean a pivot in every column. I can already see that there is no pivot in the second column. No matter what value of k I plug in, there's no pivot in the second column. So hands down, I'm going to have at least one free variable, which means that this right here is not possible. Okay, so then the next thing, line and plane, these will both be infinite solutions. We know that a line comes from having one free variable, and a plane comes from having two free variables. Okay, so let's think about the case when that 5 minus 2k is 0 versus when it's not 0. That 5 minus 2k is really the thing that's going to change things here. So if 5 minus 2k does not equal to 0, then what I have here is 1, 0, 3, 0, k, something that is not 0, 6, h minus 12. Well, in that case, that not 0 means that that is a pivot. So I have a pivot in 2 columns. I have 1 free variable. And no matter what h is, there's no contradiction because I'll have 0, 0 number and then something. Remember, contradiction is 0, 0, 0. So that's not 0. This is not having a contradiction. And I have 1 free variable. So that means this intersection in a line happens when 5 minus 2k does not equal to 0. In other words, k does not equal to 5 over 2. Now, what happens if 5 minus 2k does equal to 0? Well, that would be when k is equal to 5 over 2. Let's plug this in and see what happens. 1, 0, 3, 0, 5 over 2, 0, 6, h minus 12. Now we have that row of zeros that could potentially cause a contradiction. So here we have 2 things happening. We have no solution if h minus 12 does not equal to 0, and we have infinite solutions if h minus 12 does equal to 0. So if h minus 12 does equal 0, then I have 2 free variables. And we know that 2 free variables means intersection in a plane. So this intersection in a plane is going to happen when k is equal to 5 over 2 and h is equal to 12. Now this no intersection, that is going to be what happens when we have a contradiction. And that contradiction is going to happen when k is equal to 5 over 2 and h does not equal 12, as we just saw there. So this right here is my final solution to this problem. Oops. This is my final solution to this problem. Notice this was really a consistency condition question. We kind of just had to take it one step further. When we were plugging things in, we had to actually count our pivots. Now I want us to go back. Notice that k equals 5 over 2 is the value that showed up when we were parallel. And we said that when we were parallel, one of 2 things could happen. Either there could be no intersection because they were just parallel and not touching each other. Well, in this case, that happened when h wasn't equal 12 and k was equal to 5 over 2. So this right here is like saying my parallel planes. Parallel, but not the same plane. Or we said that they could end up being the same plane and therefore intersect in a plane. And that was also going to happen when k was equal to 5 over 2. So here, this was like saying, hey, look, these are the same plane. Good. Now, the one line thing, this happens when k does not equal 5 over 2. So in a sense, like up here, we said they're orthogonal if k is equal to -4. Well, orthogonal is going to be one of the cases where they intersect in a line. But notice it's not the only case. So they could come together and they could intersect at a 90-degree angle, but they could also intersect like that. And then that place where they're touching there is still a line, right? So orthogonal or not, as long as they're not parallel, these planes are going to come together and intersect in a line. Of course, 2 planes can never intersect in a point. There's no possible way. Okay, so I know these questions are super confusing, so I recommend really going and trying to think this through from the beginning on your own. A lot of you were having trouble with the consistency condition questions. This is one, but like on crack. It's even harder. So just make sure that you kind of understand. I recommend going back and redoing the consistency condition question on your test and then coming back and trying to rethink about this question after that. All right, good luck, guys.